Welcome back to Unit 4. We're going to continue our discussion of stoichiometry, and we are going to look at net ionic equations and qualitative analysis. In your textbook, it's page 270 or 260 to 270. By the end of this lecture, you'll be able to identify and predict reactions using net ionic equations. You'll be able to describe what qualitative analysis is, and you will be able to design a qualitative analysis procedure involving diagnostic tests. So when we look at reactions in solution, so far we've been balancing chemical reactions and treating everything as either forming compounds or coming out of compounds into elements. When we look at reactions in solution, the collision reaction theory states that reactions occur when atoms collide or ions and molecules collide. So solids and gases have a small surface area to collide, so the collisions happen rarely. If you look at solids, if you have solids, say you have two different bricks of chemical, if you force them together, they can only react along the surfaces they touch. Even if you grind them, they can only react where one compound is physically in contact with another compound, and so the reaction is going to happen much more slowly. In solution, there are more particles in one place, so collisions can happen more readily. On top of the two elements that are in solution, we're adding it usually to a bunch of water molecules, and while the water molecules may not react, they cause more collisions to happen, and so reactions happen at a steadier rate. Chemical reactions are also easier to handle when they're in solution. You can put them in a glass container and carry them around and mix them and stir them. When you're working with solids, often you don't want to be touching the solids with your bare hands, and because you can't control the reaction rate with solids, because if you have, say, two clumps of solid chemicals, they'll react at an uneven rate. So sometimes it'll react quickly, so other times more slowly. When you put things into solution, you can control how quickly things react. So the reason we use solutions is because we can control a whole bunch of factors more easily simply by changing the concentration of a solution. If we want a reaction to happen quickly, we can use concentrated solutions. If we want a reaction to happen more slowly or produce less energy, we can use less concentrated solutions. So they're safer to handle than pure substances. Often many of our pure substances might react with the air, they might react with oxygen or something like that, and by putting them in solution, it reduces their ability to react with things we don't want them to react with. So, because we work with solutions, we're going to look at something called a net ionic equation. And the reason we're going to look at it is because it's a more accurate description of a chemical reaction in solution. And we've already started looking at some of these when we did our acids and bases. When we did acids and bases, we did things like when we put HNO3, and it's a gas, into water, we said, well, what that's actually happening is we're getting some ions. The water molecule is going to steal a proton, and it's going to leave us with nitrate ions. So we already have worked with ionic equations before. We're just going to continue that kind of work here. So, based on the Arrhenius theory of dissociation, we know that solutions that conduct electricity must contain charged particles, so they must contain ions. So when we have a reaction, we're going to show entities that only change. And when we have a reaction in solution, we know that the aqueous ionic compounds break apart into ions. So because there's an electric current being conducted by that solution, we know that the ionic compound, when it dissolves, also dissociates. And so here's an example. So here we have a normal chemical reaction. It's a double replacement reaction and it's balanced. But it's good and it's accurate, but it doesn't really show what happens when we're in water. So if you take a look, we have a bunch of aqueous ionic compounds, and because they're aqueous, we know that in solution they're going to form ions. So that's the first thing we do. We rewrite all of the equations or all the formulas that are aqueous as ions. So we're going to rewrite our lead nitrate, our sodium iodide, and our sodium nitrate as ionic compounds, or as ions. And so when we break them apart, lead's a 2+ ion. We have 2, so this 2 that's down here in our compound formula ends up going out in front of the ion it's talking about. So it's talking about nitrate ions, and there'd be 2 of them. They're negatively charged. We have this 2 in front of our sodium iodide, and the 2 applies to both elements. So we have 2 sodium ions and 2 iodide ions. Once the reaction is done, we have lead iodide solid. And now because it's a solid, we know that it's not going to be ions in solution. It's going to be a powder at the bottom of the jar. And so when these two compounds, when you mix them, you end up getting a bunch of cloudy material. And this cloudy material would be the lead iodide. And so because it's a solid, the lead and the iodide are actually bonded together. They're ionically bonded together. They're not going to break apart into their ions. And so we don't write them as ions. The next thing we have is sodium nitrate. And again, the 2 applies to both the sodium and the nitrate. And so we have 2 sodium ions and 2 nitrate ions. And this here is called a total ionic reaction. Or equation. It shows everything that exists in the solution and the state in which it exists. Now, the next thing we're going to do is we're going to cancel out all those things that are the same on both the reactant side and the product side. Since they didn't change, they didn't really react, so we're going to get rid of them from our reaction. They'd still be in the solution, they're just not involved in any kind of chemical change. Just like when we have a solution, we know for most of our solutions they're happening in water, so we could write water on one side and we could write water on the other side, but there isn't much point when the water molecules aren't reacting. So since neither of these water molecules are reacting, we didn't write them down. And the same thing's going to happen with our spectator ions. So the next thing we do is anything that's the same on both sides, we just cross out. So our sodium or our nitrates were ions on the reactant side and ions on the product side, so they get cancelled out, or we don't need to write them down. The sodium ions are ions on the reactant side, ions on the product side. They didn't change. They're the same thing on both sides of the equation, so we can cross them out. When we look at lead and iodide and iodide started out as ions. They finished the reaction by being in a compound, so they did change. They were separate ions floating around in solution as little ions all by their little lonesome. They end up bonding together and forming a solid that settles to the bottom of our solution. So since they changed, those would stay in our net ionic reaction, and then we rewrite our net ionic reaction. So this one here is the net ionic reaction. It shows only those things that changed states in the reaction. So we had 2 things that were aqueous, they became solid. That's what our net ionic reaction looks like. So we'll do another example. Here we have lead acetate and magnesium iodide reacting with lead iodide and magnesium acetate as products. So same thing, we are going to rewrite our equation with all things that are highly soluble as ions. So we'll start, and so the lead acetate is ions, so we write Pb2+, and it's aqueous, so we write the state down as well. There are 2 acetate ions. They're negatively charged. We have magnesium ions, so Mg 2+ aqueous plus 2 iodine ions, and they're going to produce now our lead iodide. Just like in the last reaction, it's a solid, so we don't write it as ions because it's not ions. There's our magnesium. And finally, our acetates. And there's two acetates. And so there's our total ionic reaction. And then what we do is we go through and just cross out things that didn't change. So I look at my lead. I have lead 2 plus on the reactant side. I have lead in a compound on the product side. So lead changed. So that one we have to keep. And then we go to our next ion. We have acetate ions as reactants. We end up with acetate ions as products. Those didn't change, so they're not going to matter for our net ionic reaction. They're still there. They're still in the solution. We just don't have to write them down in the equation. Magnesium is an ion as a reactant. Magnesium is an ion as a product. So again, we don't need those in our equation. And then finally, we have iodine and iodine in a compound. So the iodide did change. And so we write down only those things that change. So we have lead plus 2 iodines goes to form lead iodide. And there's our net ionic reaction. So again, this top one was a total ionic. Or a complete ionic. And the second one is a net ionic. And so there are some steps there. We canceled our spectator ions. Those are those things that didn't change. And then we wrote the net ionic equation, and we reduced the coefficients if necessary. This one we didn't have to. If you take a look, we can't reduce. There's a 1 in front of the lead, a 2 in front of the iodine, a 1 in front of the lead iodide. We can't reduce that any further, so we're done. But we will do one where we can reduce right away. So that's how we do net ionic reactions. And here we're going to do one for zinc reacting with copper sulfate. And here we actually have to predict the product. So, before we go any further, we should predict what we're going to get. And this looks like a single replacement reaction. So, we're going to end up with copper solid. Our zinc is a 2 plus ion, so it's going to be Zn. And I'm jumping ahead here. Yep. Okay. Sorry about that. Let's get up my eraser. So, we're going to end up with zinc sulfate as a product, ZnSO4. And when we check our solubility table, we find out that it's aqueous. So we still have to check our solubility table to make sure that we know what state these things are going to be in when they're in solution. The next thing we're going to do is we're going to write down the total ionic reaction. So the total ionic reaction would be, now zinc we don't write as an ion because it exists as a solid, so it's not an ion, it's elemental zinc. The copper sulfate we can write as ions because it's aqueous, so it's copper 2 plus SO4, 2 negative, and it's going to produce, and now on the reactant side, our copper is elemental copper, it's a solid, so we don't write it as an ion, plus zinc 2 plus SO4 2 minus. Again, notice that our polyatomic ions don't break apart either. They're still polyatomic ions. The bonds inside of this ion are all covalent bonds. They're not going to break apart when they're put in water. And now we can cross out the things that didn't change. So zinc is zinc solid as a reactant. It becomes zinc ion, so it changed. So that's going to have to stay in our reaction. We have copper 2 plus as a reactant, and copper solid as a product. Again, it changed, so it will have to stay in our reaction. And finally, we have a sulfate ion as a reactant, a sulfate ion as a product. It didn't change. So since it didn't change, we're not going to write it in our reaction. It's still floating around in that solution. It just didn't react with anything. So we have zinc plus copper 2 plus, goes to form copper solid plus zinc 2+. And there is our net ionic reaction. So here we have a reaction between HCl and barium hydroxide. So the first thing we need to do is get some products. When we take a look, we can see, well, this is an acid, and this is a base. So it's going to be a neutralization reaction, which is really just a double replacement. So we're going to say that this goes to form barium chloride, and it'll be BaCl2. And when we take a look at our solubility table, for chloride, we can see that barium chloride is aqueous. And we're going to end up with our hydrogen and our hydroxides, and they're going to go and form water. So H2O, liquid, and now we have to balance it. I have 2 chlorines on my product side, so I need 2 chlorines on my reactant side. That's going to end up giving me 4 hydrogens total. So for 4 hydrogens total, I need a 2 in front of my H2O. That should balance things out. That gives me 2 oxygens. I have 2 oxygens on my reactant side, and my bariums are 1 and 1, so life looks good. And the next thing we're going to do is we're going to write out the ionic reaction. So now, as ions, we're going to write these as H+, and we could write it as H3O, but we don't need to for this reaction because it just makes things a little bit more complicated than we want. So our acid is going to form hydrogen ions and chloride ions. Our base is going to form barium ions. And there are 2 hydroxide ions, so we can't forget that 2 out in front. So there's our reactants in the state they existed when they're in solution. And now our products, we're going to have barium 2+ plus 2 chlorines or chlorides. And water is not going to dissociate in water, so we write it as a liquid. And so there's our balanced total ionic reaction. And now we cross out the things that didn't change. Oh, and it's not balanced because I forgot about that 2 that was in front of my acid. So make sure it's balanced. It should be balanced. Each of these reactions we write are going to be balanced. If your normal reaction or our normal equation is balanced, then at every step beneath that, the reaction should be balanced as well, or the equation should be balanced as well. So here we go. We're just going to cross out the things that didn't change. The hydrogen did change. It went from hydrogen ions into water molecules. The chlorides didn't change, so we'll cross those out. The bariums didn't change, so we'll cross those out. And the hydroxides did change. They were hydroxide ions. They became part of a water molecule, so our net ionic reaction is this one. And it goes to form 2 H2O liquid. And now we can check our coefficients, and because they're all 2's, we can divide this whole thing by 2. So if all of your coefficients are even or multiples of a certain number, then we can divide that number. Here we're going to divide everything by 2 or multiply by a half. It means the same thing. And when we do that, we end up with hydrogen ions plus hydroxide ions go to form water molecules. And we kind of knew that already from our previous unit, but here it's just showing us how we can get the same answer by using a net ionic equation. So there's our net ionic equation. The other ions, the chloride ions and the barium ions, are still in that solution. They're still floating around, but they didn't change. They didn't react with anything, so we don't have to write them as part of our equation. And now we're going to kind of talk about what these equations are kind of good for by looking at qualitative analysis. So we know that if there are ions in solution, sometimes those ions can cause the solution to be colored. And if you take a look, and we'll use the 2008 data booklet, from the 2008 data booklet, if you look at page 11, you'll see a table showing you ions in solution. So they give you the ion name, and then there's two columns. The middle column is what color the solution will be when it's in high concentration, and the right column tells you the color when the solution is in low concentrations, or when that ion's in low concentrations. And so an example would be if we just take a look at the chromate ion, which would be CrO4, and it's 2 negative, I believe. Now I gotta check because it slipped my mind. So I'm just gonna go to my polyatomic ions in my periodic table, and chromate, yeah, it's a 2 negative ion. So when this is in solution, so when it's aqueous, when it's in high concentration and low concentration, it has slightly different colors. At high concentrations, at concentrations of 1 mole per liter or higher, sorry, I just lost my page in the book here. Alright, it's going to be yellow. It's going to cause the solution to be yellow, so it'll be clear, but it'll be yellow in color. It'll look like lemonade. When it's in low concentration, it'll be pale yellow because there's less ions. And so you'll notice on your chart that the right column here, it's usually the same color that's in the middle column, but just a lighter version or a less concentrated version. So, for example, things that are blue-green might turn green because the blue starts to disappear. Things that have light colors, like if you look at iron 2 ions, when they're in high concentration for iron 2 ions, it's lime green. When that concentration starts to get lower and lower, eventually it becomes colorless because lime green isn't a very, I guess, strong color to begin with. So that's the way that table works. So sometimes we can tell what's in solution by its color. Other ions produce a flame of a specific color. So the way you test this is with the flame test, and you can take either a drop of solution or some precipitate. So sometimes you need a chemical reaction, you get a solid in the bottom, and then hold it over a flame. So in a chemistry lab, it would be a Bunsen burner, but you hold it over a flame, and that flame will burn with a particular color. And now, if this table is actually on a separate page, it's not the same table that's on page 11. This table is actually on page 6 in the 2008 book. So in the 2008 book, it's on page 6. And both these tables are exactly the same as the tables in the 03 book. They just might be on different pages. And so there's a list there. It says flame color of elements. And so if you have lithium ions in a solution, or lithium as part of a compound, when you hold it over a flame, that flame will turn a red color. If it's something like copper, if you hold copper ions over an open flame, so either copper ions in solution or a compound with copper ions in it, it'll be a blue or green flame. So you can kind of get an idea about what kind of ions are in a solution by what color of flame they produce, or what color of flame they produce when they're held over an open flame. One of the most useful tests is insolubility. So some compounds are insoluble in water. So if you think you have an ion in solution, you could try to make it react with something that will bring it out of solution. And we'll look at a couple examples of that here. So if we have sodium acetate in solution, we have a clear colorless solution, and we're going to add sodium acetate. When we do, a precipitate forms. What ions could be present in that solution? So here's the idea. We're going to take sodium acetate. Now sodium acetate would be Na plus ions when it's in solution, plus acetate ions, which would be CH3COO negative. Now we're adding it to a solution with some unknown ions. There's going to be a positive ion in there, and there's going to be a negative ion in there as well. Maybe we should put the question marks over the blanks since we're trying to figure out what's in that solution. So there's going to be a positive ion, we don't know what it is. There's going to be a negative ion, we don't know what it is. After the reaction, we get a precipitate, so we get a compound. And so the question is now, we get a compound, there's also going to be some positive ions in solution, and there's going to be some negative ions in solution. And what we're kind of doing here is, we know that a double replacement reaction is taking place. Something from that sodium acetate reacted, and the sodium and the acetate switched partners with two things that we don't know yet. So we can go through, and what we do is we're going to look at our solubility table. Since we don't have any colors to look at, we're going to go to our solubility table, and we're going to take a look, and we're going to say, well, what could form a solid compound with, say, sodium ions? And if you take a look at your solubility table, at all the negative ions that are listed on the top, none of them form a solid compound with sodium. So sodium never forms a precipitate. And that's why when we're doing this kind of qualitative analysis, when we're trying to find out what's in a solution, we often, if we think we have a positive ion in solution, we're going to react it with something that contains sodium, because the sodium is just going to go into solution, which means that whatever was in that solution reacted with our acetate. And then we take a look at our acetate ion, which is just in the first column, the second column there, and there are not many things that can form a solid with acetate. Most things don't. The only things that do are silver. So we could get AgCH3COO. That's one possibility. The other possibility is mercury. So CH3COO2, and it's mercury 2. So that means this positive ion can only be silver or mercury 2. Those are the only two possibilities. One of those two ions are in our solution. And so even though we didn't get down to one thing, we got it down to two, which is pretty good when you consider there's over 100 elements in the periodic table. We've narrowed it down to two that could possibly be in this solution based on a chemical reaction. We still don't know what this is, and there's no way to find out by using sodium ions, because sodium doesn't form a precipitate with anything. And so in our solution there'd be some leftover sodiums, and again we still don't know what this is, because this ion and this ion are the same thing. But we do know that there's either silver ions or mercury 2+ ions in that solution. If we wanted to determine if a solution contained chloride ions, so for chloride ions, and here's the question we're going to ask. What can we react with chloride ions? So what positive ion can we react with chloride ions to bring it out as a chloride in a compound? So the idea is we want to find something that's going to react with chloride, or react with chloride to make a solid compound, but it won't react with anything else to make a solid compound. So what we do is we're going to check solubility table, in your data book, it's on page 6, and we're going to look in the chloride column. So the column that has Cl negative, Br negative, and I negative. And when we look in that column, we see that most positive ions form soluble compounds with chloride. So those ones wouldn't help us. If we added them to the solution, the chloride ions would stay aqueous. But if we look at that bottom row, we can see that copper ions, silver ions, mercury 2+ and mercury 1+, and lead all form precipitates, or all form solid compounds when we react them with chloride. And so any one of those things would do. So we could say, well, we want to add copper, and it's copper 1 plus. So copper 1 plus ions, and that would give us copper chloride solid. So we could add copper ions. Now, we can't add an ion by itself because ions don't exist in solids. So to add the copper ions, we'd have to add a copper compound. So by adding a soluble copper 1 compound, such as, and my favorite is copper nitrate. Oops. Copper nitrate. Now the reason you add copper nitrate is because you know that the copper nitrate is going to be aqueous, so any solid that forms in your solution won't be with the nitrate ions. Nitrate doesn't form a solid compound with anything. It only exists as an aqueous thing when it's in water. So when the precipitate's formed, or when the solid's formed, you know it has to be a solid containing the chloride ions and not the nitrate ions. And since it contains the chloride, you know it's going to be the chloride and whatever positive ion you put in there. So this is qualitative analysis, and it's used for things like identifying the presence of substances. And it's used for breathalyzer tests. It tests for the presence of ethanol, and these are the roadside tests where you blow into a little device, and if there's ethanol in your breath, then, and it actually be ethanol anywhere in your lung cavity when you breathe it out, it'll react with a known compound to produce a known result. And if that result happens, then you lose your license and all the other bad stuff. It can also be used for testing drinking waters for impurities, or it can be used for testing the chlorination. If you want to make sure that your water has enough chloride in it, to make sure that it's clear of bacteria, it can be used to test, say, iron levels or mercury levels in drinking water, especially used if you have well water. It's also, another example would be one of a litmus paper. Litmus paper is a qualitative analysis. When you dip litmus paper into a solution, if that litmus paper changes color, you know that you have either an acid or a base, right? If you have blue paper, if it turns red, then you know you have an acid. If you use red paper, that has to be litmus paper, of course, if it turns blue, you know you have a base. And the same works for if you have, say, blue paper. If it stays blue, then you know it's not an acid. It's either neutral or a base. When you use red paper, if it stays red, then again, you know it's either neutral or an acid. And so by using a piece of blue and a piece of red, you can always tell the pH of a solution. You can tell if it's an acidic or a basic solution or a neutral solution. If you have one solution and you test both paper colors and neither of them change color, then you know you have a neutral solution. So a qualitative analysis is the idea of taking a reaction with known results and applying it to a situation. If the result occurs, then you know the substance was there. If no reaction occurs, then the substance is not there. So what we're going to be doing is we're going to be testing for the presence of ions, and by using reactions that we know produce a result. So for example, if you want to find out if a solution has calcium ions, we know by looking at our solubility table that calcium and sulfate react to produce a solid. So what we can do is we can add sulfate ions to a solution. If a precipitate forms, then we know we have calcium, because on our solubility table it says that calcium and sulfate form solid compounds. The same can be said with our chloride ions, and we just did that example, but the same idea. if we're looking for chloride ions in solution, we're going to add something that we know produces a result. So if we add copper ions, then we know that, or copper 1 ions I should say, if a solid is formed, we know there's a good chance that chloride ions are there. If no solid is formed, if the solution stays clear, then we know that the chloride ions are not there. So, and we can do this for any type of ion that we're looking for. So the first thing is you have to know what you're looking for, which will be given to you in a question. And from that, we're going to choose chemicals that we can add that will produce a known result if the chemical is there. So here's an example. We suspect a sample of water may contain sulfate and or aqueous chloride ions. So we're going to design a diagnostic test or a series of steps in order to find out if these things are present. So we're going to start with just drawing a little flow chart here. We're looking for whether or not there's sulfate and or, so it could be one, both, or neither, and chloride ions in a solution. And so then we're going to take a look at our solubility table, and we're going to find out if there's something that will precipitate one of these but not the other. So we want to precipitate only one of them but not the other. If we use something that precipitates both, if we add that, we won't know what is in the solution. It could be that both are in the solution or only one, and because it would precipitate either, we're not going to know which. So we only want to find out one, or something that will precipitate out one of them or form a solid with one of these ions but not the other. So we take a look at our solubility table, and so we're looking at sulfate and chloride, and we can see that most things, if we look at that second row, most things stay aqueous with either of those ions. If we look at the third row, the bottom row, we can see that there's 5 ions that form a solid with chloride, and 2, 4, 6 ions that form a solid with sulfate. And the idea is to pick an ion that's only in one of those columns. And so, for example, silver would be a bad choice. Silver forms a precipitate with both chloride and sulfate. So silver at first, so silver ions are a bad choice for the first test, because we won't know what we get. If there's a solid, we won't know if it's silver, sulfate, or silver chloride. So we won't add silver, but we could add copper 1 plus. So here's what we're going to add. We're going to add copper nitrate, copper 1 nitrate, as a solution. If we get a precipitate, so there's 2 possibilities. If we get precipitate, and if we don't. If we get a precipitate, we know that there's chloride. Chloride ions are present because they form a solid with the copper. If there's no precipitate, then we know that chloride ions are not present. So the next thing we would do is, if they were present, we'd remove the solid, and we do that by filtering it. And then we go and we start our second test. So now, the only thing that will be present are SO4s, because the chloride either wasn't present, or if it was, we removed it once it reacted with the silver. So now we look for a test for our sulfate ions, and now we can use pretty much anything that's in that sulfate column, because the chloride's already been removed. So we could use silver, we could use lead or mercury, any of those would work now, and if there was a precipitate, it would be just with the sulfate. I'm going to add calcium ions, because even if there was something else there, even if there were chloride ions left behind, the chloride ions don't form a precipitate with the calcium, so it's probably our safest choice. If there's a precipitate, then we know that SO4 2 negative is present. If there's no precipitate, then SO4 2 negative is not present. And that is an example of some qualitative analysis. It's checking to see what might be in a solution, because we can't tell just by looking at it. So there's a prettier picture, and this one was done in the reverse order. So in this one, or in this flow chart, there was a test for sulfate ions first. That's why they added calcium nitrate. And again, we just chose a negative ion that will never form a solid or never form a precipitate. And then after that, they tested for chloride ions, and same idea. So that's an example of qualitative analysis. There's a couple of examples on page, or practice problems on 264, and a thought lab. Try out the thought lab on page 267, and there'll be an answer sheet posted for it on the WebCT.